Hello, everyone. I'm very excited to present this workshop about Juvix. It's a really interesting project. It has many ideas. It has evolved during this last year. My name is Jonathan Cubides, and I also prepared this with Paul Cadman, which unfortunately couldn't come today, got sick. And all right, let me try to say a few of the goals that I have for this talk. I want you to understand what is Juvix, why we are building this new programming language for ANOMA. And I believe we can use Juvix also for other different purposes. And in particular, since we are here in ZK Summit, I would like to just present a little bit about the compiler infrastructure to support zero-knowledge proofs. And my main objective today is that you can try Juvix yourself on your machine, so I hope you can open your laptops and try with me all the exercises that we prepare for you. All right, before delve into the specifics of the talk, I believe it's important to just mention the people that is behind this project. We are a group of 5. We are mostly just mathematicians or computer scientists with a background in formal verification and type theory. This is my team, is Paul Cadman, Jonathan, it's my name, and Lukasz Shaika, and Artem Gurev, and Jan Mansrovira. That's the team. So in very short terms, Juvix is this high-level language that we have for writing ANOMA applications. We are designing this language to have privacy-preserving decentralized applications. And I would like to give some context, will justify why we are creating this new programming language. So ANOMA, this is the definition of ANOMA. It's an intent-centric architecture for decentralized counterparty discovery, solving, information flow control, and atomic multi-chain settlement, right? And I just said that Juvix is this programming language that you are going to use or that you can use to write applications for ANOMA. So for improve the understanding of ANOMA here, I prepared this. So ANOMA is based on the concept of intent. So this is really central. It's a primitive in this context. And an intent is basically just a message that expresses how you want the state change, right? So it's a high-level description. It's a program that encodes your preference about how the state's going to change. So we have here, this is a simple example of two-party exchange, right? We have 3 actors in this. We have Alice and Bob, and Alice has the intent. He wants to get 1 unit of dolphin and is willing to trade either 1 unit of item A or 2 units of item B. That's Alice. And we have Bob, who has also the desire to trade 1 unit of dolphin for, and it can it can trade 1 dolphin for 1 unit of A, right? That's the preference. And we have in ANOMA a component that is called Taiga. Taiga is a framework for shield transactions, but is the component in ANOMA that is in charge of dealing with these intents. And there is another concept that we have in Taiga that is called partial transaction. So before to submit any transaction to the blockchain, we need to prepare it. And the way that we need to do that is to create partial transactions. And once you encode that in something that Taiga can't handle, we put this into a gossip pool where all the intents go. And there is another component in ANOMA that is the intent solving. So we have solvers And solvers are basically just algorithms or that can be users as well, or just other programs. And these solvers, they can unfold information about the about these intents, about this partial transaction, and there are some other specifics that you can use in order to get a matching between the preference of Alice and Bob, right? And once you find a matching, then you can get the finalized transaction and submit that to ANOMA. Of course, I'm oversimplifying many details here. If you have any questions regarding the cryptography, I have here my colleague Alberto, who is the person that is designing Taiga as well, and yeah, all this concept of intents. Me, with my team, we are just developing the programming language. So the programming language looks like what you have on the right. So we have an API for Taiga, and you should encode every intent in what we have modules here, right? So I don't really expect you fully understand all the encoding here, but as I said, an intent, you need to encode it as a partial transaction. For example, Alice, I said that is willing to trade 1 unit of A or 2 units of B for 1 dolphin. So in Taiga, you have these two pair components of a partial transaction. So you said what are you going to consume and what is going to be available later. That's the created pair, right? So you can see here that you have 1 unit of A or 2 units of B, right? And we have another encoding for the Alice intent. So this part gets a little bit more trickier because you need to encode the logic, which are just the conditions for your transaction to be valid, right? So you can express this using this predicate, which is just a function that gets value into bool. And there is this encoding, by the way. Just taking this example from the documentation, so you can just go to docs.juvix.org and just follow this. All right, and there is other components. And also, if you're interested how exactly the transaction lifecycle is, we included like a client-server sequence diagram for you to understand. This is the long term. This is like the main goal for Juvix, is to be the language in which you can write these intents to able to create these transactions on the ANOMA blockchain, basically. Right. Okay. Let me go back to my. So that's the reason why we're creating a new programming language, and it's important because ANOMA itself can be seen as an operated system, right, where the primitive notion is the intent, and as any other operated system, there is a notion, a model computation, which is not the same as the computer that we're running these slides. So those details are what make a special Juvix, because we are targeting a different model of computation. But the specifics, I'm not going to go into the details. ANOMA and Juvix are these two projects that are on heavy development, and we are figuring out all the details about how to make the things work, right? Yeah, so these are our 3 main goals for Juvix. And we plan to be a language jointly with the compiler of yeah, for ANOMA, basically, right? Yeah, these are our main goals. However, while developing the language, we are not really limited to ANOMA. We are actually reaching the point where Juvix can be just a general purpose programming language. And as I said in the beginning, we have a pipeline that compiles to zero knowledge proof, which I believe is what you are here. So our compiler starts with a file that is written in Juvix. This is the extension. And we perform different static analysis. Of course, we need to parse the file. And we have a type checker. And we have this Juvix core, which is the main core language. Is just an untyped lambda calculus with some extensions and some optional typing. And for this intermediate representation, we have backends. We have native binary output. We can deploy to WASM. We have these in-house compilers that are called VampIR and GEP. And the purpose of these two backends is to produce zero knowledge proof, right? So I was checking on the log of ZK Summit, and I found that there are some talks about VampIR, so you can check it out online. You take Juvix and you generate VampIR code. And this is our in-house compiler that can produce Halo 2 circuits. And it's basically a proof system agnostic compiler, right? We have currently just support for Halo 2 and Plonkish circuits. So let me talk about a little bit the language itself. We decided to create this language in the same fashion as ML or Haskell. So Juvix is just another language in the ML family. And the main reason is because the intents are just declarations about your preference, right? So you specify exactly what you want, but you don't specify how. This really matches with the declarative style of programming. And something that we decide, like this is our design choices, is the language is static, strongly typed, and the evaluation strategy is strict. So we have strict semantics. And we're just taking feature from the mainstream languages. So we have purity, we have totality. So we need, we enforce your functions and your data type declarations to pass certain static analysis. You have immutability, pattern matching, traits, referential transparency, so on and so forth. So so Juvix is just this functional language is Turing complete by certain annotations, and you can go to the documentation. We have provide reference of the many constructs of the language. And if you are more curious about the specifics of the language, we are also making some specs, some formal specs about the language. Right, okay. It seems like I don't have internet here. Yeah, okay. Yeah, so we have in the language these characteristics, which is referential transparency. You expect that a program with the same inputs produce the same outputs. That's something that you expect. We have a module system, so you can modularize your program. You have top and local modules. You can you have these open import statements, so you can bring to scope different identifiers, names, and you can select imports. You can hide things. We also have a red REPL, so you can interact with the language. And we're very proud of this documentation tool. It's really nice. You can just, in the same way that you put comments on your code, you can put doc strings or kind of what you find in Haskell with Haddock. I'm going to show all these things quickly. And we are just building an ecosystem around Juvix. So we have a few libraries already. And I really expect at some point people will start contributing to the ecosystem with your libraries. We need cryptography. We need many other things, right? So at the moment, we just have support for data structures. We have property-based testing, a la QuickCheck, right? And we have a unit test framework if you want to do. All right. So may I ask how many of you are willing to try on your machines Juvix? I hope. Yeah, I will try it. So the idea is just to go like a very high level. I will not go into the technical details. Everything is in written form, so you can just find it on the website.
When you press the install Juvix on your machine button on the website, it goes to the local host link.
Oh, really?
So I'm not running your server there, so I can't.
Ah, all right, all right. Yeah, probably. Okay, let me. Okay, those are things that need to be double checked before. Right. So this is our documentation. The colors are not really like you can see here. Right. So we have two options. You can install on your machine. We have support for Homebrew. You can install the binary directly. There are many ways that you can install Juvix. And for this workshop, we also have a code space. So you just click here, and this will open on your browser Juvix with all the environment in Visual Code. But so right, so this. Oh, yeah, I saw your comment. So in the documentation, we have installing Juvix, and basically you just can copy and paste this on your terminal, execute this, and you will install Juvix. Otherwise, you can have Mac Homebrew utility, right? Okay. But I really like this code space, so let's just try this. And by the way, I included in the tutorials, we have this ZK submit, right? So let's try to follow this tutorial all together. So the first thing is to install the Juvix compiler. If you want to just skip this process, just clone this. This is the source of the workshop, right? Okay, so when you're creating the code space, you just click here. It will take a few minutes, I think. Well, okay. While this loads, let me see if I can say a little bit. Right. Okay. Is there any questions so far about the language? I haven't really shown the zero-knowledge proof thing, but I'm going to do it. The main intention for me today is that you get familiarized with this language and that you can leave the room knowing that there exists a new programming language that you can use to compile to zero-knowledge proof. It's a high-level language, and we are solving a lot of the problems that you face during circuit compilation. There are very few. And okay, so yeah, this is just building. Okay. So if you have on your machine Visual Code, you can go directly and just put here Juvix. This is our extension. And then you just need to install it. And something nice that we put here is that you don't need to really install the binary of Juvix. It will do it automatically. And it will also install the binary for our in-house compiler, the VampIR one. So you also have that problem solved. Once you install that, my recommendation is to open a new folder where you're going to put your files, because the extension needs a workplace inside for your files. And yeah, so the first thing that you want to see is hello world, right? You want just to see how to encode hello world. So every file defines a module, and the module name is exactly the file name. So you need to use the same name. It's hello world in this case. And this is a bit of the syntax. I just want you to try this on your machines and just execute. We include these four buttons, actually. With this one, you type check the code. So you check that your terms actually correspond to the type you are annotating with, right? And you have also compile, because you can compile your program to different backends. By default is the native. And you have also the play button, so you can run this. So in this case, you will just see here, hello world, right? And for example, as I said, we have this documentation. Let me try to see it. Exercises. That we include, yeah. So the documentation just starts with 3 dashes. And in Visual Code, you just can press this button, HTML preview. It's on the top. And you get a nice looking documentation. I'm going to try. So you can use this to document your programs. And this is a web version of the Taiga simulator, which is the example that I show about the intents at the beginning. What is nice is that you just can click. If you don't know anything in the code, you just need to click on the identifier, and that will take you to the definition, right? So, for example, here in the I know my intent API, a resource is this record type. So you have 4 fields. The first one is a logic hash, which is just it's just an address that encodes where to find the predicate. You can have other data types, other values. And yeah, so this is more or less how it looks. And I'm gonna try to you to try this on your machine. Okay. So this is Visual Code. Let's check it out if the Visual Code. Yeah. So this is the code space. Just let me change the color theme to something. I don't know. The light is better or the dark? Light? Light? Okay. Perhaps this one. Okay. Actually, let's just double check what we have in the README. Just want to make disappear this. Oh. I had, okay. Yeah, okay, so we have workshop exercises. Good. 1 second. All right, so in the code space, and if you follow the instructions, after doing the installation, you can just execute from your terminal. So here in your terminal, you can have Juvix. It's just another, this is the CLI. And you have different options, right? So you can type check your code, you can compile it, eval, and generate the HTML. Or something that we also include is this command doctor checks if you have everything set up correctly. You can initiate a project, and there are many other things that you can do. For example, if you're interested in compiling to zero-knowledge proof to circuits, then you will go and write compile and then put compile help, right? And then you have other options, right? And you will be interested about the target. So we have all these targets at the moment. We have WASM, we have assembly, native, we have Geb and VampIR, and core and ASM. In the code space, you also have access to the VampIR code. Sorry. With this. So VampIR is the one. It's like our low-level, high-level language for writing circuits. So before you write Hello 2, you can just use VampIR, and it will abstract many details that you don't need to know. It has support for higher order functions, and there are many things inside this compiler. And then you can work with Plonk, Hello 2, right? But we want to do that in a moment. All right. So this seems like we have everything set up. All right. ZK submit. Something as developers we're used to also to interact. So you have this button over here is the one that loads the file in the REPL. Also, you have this option. And yeah, and if you click on this, this will open a terminal. It loads the module, and then you can ask things like, you can ask, for example, what is the definition of booleans, because I don't remember. So then you get this nice output. And also, as I said, if you don't know anything, you just can click on an identifier, just press command. And we actually have two things. So you can, let's just close this terminal. You can, with your mouse, hover the identifier, and then you get this, this information, right? For example, it tells you that this NAT type is just an inductive natural numbers definition, right? And then just pressing command or just with the mouse, you can go to the definition. You can jump and see exactly what the things are, right? The definition itself.
Where are these files in the file system?
Yeah, so with the compiler, we ship also the standard library. So you don't need to care about installing standard library. You just start importing it this way. But yeah, let's go step by step. I'm just trying to show an overview of all the features that you have if you use Visual Code. We also have support for Emacs in case you are an Emacs user. But today I'm just using Visual Code. Okay. There are many things. We're trying just to ship to make a programming language with all the advantages that you will find in any other high-level language, right? So let me go for probably the most essential things, right? Which is functions. So in Python, you will define a function using the keyword def, Well, in Juvix, you don't need it because you are just defining so many functions. So we decided to just drop that keyword. And the first part of a definition is the name of your function. You can have arguments and then put a name for that argument. And always put that type of notation. So that goes after the colon. So in this case, we're defining a function that takes as an argument a natural number with the name n and produce an output of type natural number. What is a natural number? You don't really need to know. But if you want to know, then you just, in your code, as I said, command click, and then you just go and see the definition of it. Okay? All right. So if you write this, well, this is a function and it's incomplete because you haven't defined it, the body of the function. So you need to define what the function does, right? And for that, we have this assignment symbol. So after this assignment symbol, you define what exactly your function does. And we have many language features to define this. In this case, we just want to add 1, right? So try to code yourself on your machine this function. It's just add 1, and then you define n plus 1. Let's try to do it all together. So I'm going to open a file. I'm just going to name this put here Juvix. The extension will suggest to insert the module name. I'm just going to click. And after clicking, I'm going to define the function. So if I do add 1 and put, for example, nat, this is incomplete. I just configured a shortcut for the, so you can click here on the check symbol to type check your code. And then you get this error message, right? Where what the error message is saying is that it's expecting the definition of the function. So we need to use the assignment symbol. Oh, and then I have the copilot, so it can learn how to code Juvix already. You just can put equals 1, and this is, perhaps a name for this will be 1, right? But it doesn't know what is not. So we need to import the definition. So we have a standard library. It's called standard lib. And then we have a prelude with all these definitions. And it tells you, well done. It type checks. This is like the reward for you. Now let's define this function at 1. And the type signature can take different forms. Look, this copilot is already too smart. You can use it. One thing about the visual code is that we have support for Unicode. So if you press the \/ then you can have really nice things like alpha, beta. You can put really nice things. But yeah, so what I'm doing here? Oh yeah, okay. I'm just taking a number. Let's call it x or n. Doesn't really matter. And then just x plus 1, right? We have, or you just can do it directly. Well done. Okay. This is how you define a language. We have other constructs. You can define the maximum between two numbers. The way that you do it is that just put a name for the two arguments, put the type signature saying that the maximum of two natural numbers is just another natural number, and you can use the if. So you have this comparison here, and then you return what is the maximum, right? We can just copy this from the from the documentation, click here. Right, so you don't have, you need to import this. So we need to import data, not, or the open. We need the relationship, Okay, this type checks. I'm gonna try this right away. I'm gonna use the REPL, and I'm gonna do maximum between 1 and 6. It's 6, of course. Again, if you want to know what is maximum, then you have the definition. All right. I think something that we inherited from the ML family is the definition of function by pattern matching. This is really convenient. So a definition of a function by pattern matching is telling you, well, it's introducing equations for the definition. For example, in this case, we want to check, I don't know if this is big enough. We want to check if a function, if a natural number is 0 or not, something that you will encounter in circuits. Well, you can say the natural number can take 2 forms. It can be 0, and in that case, you just output true value, or it can be the form of a successor of a natural number, right? And in that case, you output false, right? This is the way that you split out the definition of a function. And you just can take this and type check if you want. Well, okay, here it is telling me that I don't have booleans, so I need to include booleans. But sorry, it's actually about this. We are changing the syntax to make it simpler. So, right, let's terminate this. Good. And you also have support for recursion. So if you want to check that a function, that a natural number is even or it is odd, you can formulate this function introducing these 2 equations. 0 is an even number, so you just output true. And if it's a successor, you ask the same function to respond the question, but for the previous number, right? So you can have also this. You can type check. We're again with the semicolon. Can make this appear this. And something really nice about programming languages, especially functional programming languages, is that you can define the parametric type of list of elements of different type. So we have support for polymorphic pre-next polymorphism. So we have we can define the type of list of a natural number, the type of list of strings, and list of lists, so on and so forth. But we already have done, so you don't really need to do this. We are just declaring a lot of functions. We have libraries that already provides all these implementation details. Here we are, here it shows up the polymorphism. So you have a variable A. This is a type variable. It's an implicit one, so you don't need to provide it. It will calculate the length of the list. So the argument of the list, the argument of this function is a list. It can take 2 forms. It can be the empty list, in which case the length is 0, or it can be formatted by or consist of one piece of data of type A and with another list, right? That's the constructor of a list. And then you have, just using recursion, the length of this list, for example, is just +1, right? So you can use successor or +1, and then calculate the length of the sublist in the case. And we are really excited about this language feature. We can change the syntax. There are many things that we can do. Let me just reference where exactly you can find. So we have some syntax extensions in the documentation. You can put aliases to things. So if you want to name, I don't know, let's say that you don't want to use bool, you want to name Boolean, that type, you just can put syntaxes, aliases here. You don't like false, you want to be very logician, so you use the Unicode term. You can do these things. What other things? We have iterators. So it's not really usual to find these extensions. I actually haven't seen this in other programming languages. I like to Juvix. But we have this iterator syntax. We can tell, I'm going to define an iterator like a for loop that goes from a starting point here and goes to other bound, right? Another syntax extension that we have is fixity. So you can define different fixities. This is more like if you are defining your own operations and you want to be a binary, you want to define a binary function that is associated to the left or to the right, or that is equal to some other operator. And then you have lattice, basically, to resolve the syntax. So that's another facility that we're including. And we are also having this operator syntax to, in this case, this is very nice in my opinion. You are defining the type, the product type, which is just taking two pieces of data of different types. The constructor is just the parent, right? The type for the constructor is just a function that takes something of the type A, something of the type B, and then you construct a term of the product type. Well, here you're using this time symbol. This is really nice, but you can say, okay, this time symbol is just another operator for the product, and the product is just a binary operation. And then you are free to go. You can use the time symbol everywhere, and this will resolve. Again, if you don't know anything or you just miss something that I said, you just use the search bar. You can go for operator here, and then this will take you exactly to the place. We're trying to document all the things you can do with Juvix. All right, let me see what else do we have. Pattern matching, polymorphism, iterators, yeah, right. And then we have the exercises. Okay. So how would you define a function that takes a list and sum up all the elements in this list? Well, it's a function, let's call it sum. The argument, let's call it XS, and then you have the type of this is the list of natural numbers, and because you are summing up, you are getting a value of the type nat. This is the type of natural numbers, and then you need to define some way to do it. So the way that you can do it is using this iterator syntax. We have this for, so you said, okay, I'm going to define a for, similar to Python a little bit. You have an accumulator. This is a variable where you can put values in it. And then you can iterate in the list. This is the syntax. You say x in the list XS. And then in the accumulator, you can put this value, which is the element that you are currently visiting, plus what you had before accumulated, right? This is really nice. nice. Because you then can simplify a lot of the common function that you will find in functional programming languages. You would usually use fault, left, right, and that. Well, it's really nice, but we already have these convenient functions.
I have one question.
Yeah?
Is this like fully statically tied to compile time, or can I have like runtime with a list of any objects and I determine through some discriminated union what it is at runtime and then apply the code from there, or is it?
Yeah, it's statically typing.
So it's fully statically tied at compile time?
Yeah.
Okay.
Yes. Yeah, and something that we are trying to enforce, at least for now, is that typing is, as I said, is required. So it's like a discipline. Maybe it can be seen as a drawback, but in the long term, it's a good investment for you and for the sake of your users.
Is there type inference?
Yeah, we have a type inference. So the core language is actually untyped lambda calculus with an option at typing. And we have underscore, so I can. So in some places you can put, for example, let me see, this works. For example, here, right? So you can infer what is the type of 1, right? This is fine. So we have an algorithm that we have type inference, right? But you cannot skip the typing. And by that is, what I'm trying to say is that you cannot skip the colon type. But we have this underscore, which is the device that you can use as a placeholder. You can ask here, for example, what is the type of 1? So let's do it. So you can open the REPL here. And then I think it was colon T, but let me double check. Oh no, it's colon type. Okay, so you click type and then 1, and then you get not. And if you are disciplined, so you put here not. So you can interact with the REPL and try to make your program well specified. I think it's a good discipline. Also, I'm a fan of type, so.
So, I mean, in the maximum example, if I replace both of the nats with 3 of the nats with an underscore, and then I can apply that to anything that supports the comparator.
Right. So this in particular, you can see that I'm just getting the definition, and you have the 2 arguments nat. So in that case, I can infer that as well. Yeah. There are other places where it gets more challenging. So
I'm thinking more like macros, templates, if I have the same algorithm, and I want to apply it to different, like, I'm really worried about, like, with VampIR, and it just spits out, 40 gigabytes of type inference code, not type inference, but different states they could possibly be in. And if I want to be very specific with the underlying types that I'm using, but have like 2 versions where one runs on 128 bit, the other one runs on prime field.
There is a step going to VampIR that we need to monomorphize the code, and so we will be very explicit about all the types inside the type signature. So yeah, there is no so much room to screw it up here. Right. And things that you will find, I'm really sure that this will become really mainstream in the future, is mapping and filters, like this functional programming paradigm of these facilities that we are shipping in Juvix, and you can find in Haskell or Camel or Coq and Lean. This will show up in all other programming languages. You have mapping. You just sent out. This is just an abbreviation for a function that just takes a list and then you evaluate the function in every single part of the list, or you can filter out things. So, yeah, this is the syntax. I think it's a really nice thing for you to try. So we have these exercises. We have 10 minutes, so we can probably pick one. Let's try to do the exponentiation, right? Or you also have maybe things. So you're not missing anything here. Everything is going to be online. So if you cannot follow the tutorial today, just sit down next day or whenever is better for you and just follow the tutorial. So if we try to do the exponentiation exercise and you download this, we have this file. Maybe you didn't notice, but we have a statement to introduce things without definition. And we call that axioms. So if you don't know the definition of a term and you want to use it, you can put axiom. That basically tells the compiler that that term doesn't have any computational content at the moment, right? And if you later find out what is the definition, you just can remove the keyword axiom. So if you have exponentiation here, let's just try to define this. Right. So how would you define exponentiation? Let's say that the first argument is the base, and the second one is the exponent, right? I would like to be the secretary here. So if someone tells me okay, so this is exponentiation, takes two arguments, x and n, and we're gonna do it in the same fashion of pattern matching. So you need to pattern match on nuts. So, so you have x and then you have 0. What is the result? Oh, we have the copilot that just says as 1, right? All right. If you, man, you can use the copilot and just write the definition for me. Right, you don't need, okay, the copilot screw up here. So if you have x and you're trying to have n plus 1, then you just need to multiply the recursive call of x with n. And then you're free to go. It's not suck with double C, it's just with one C. What is going on here? Let me double check. We probably gonna change. Oh, sorry. Right. Well, actually, yeah, there is no need for putting this x. What is going on? The column, yeah, semicolon. No, there is something wrong. Well, that's why you prepare the solution in case you cannot handle it. Oh, yeah. So one thing is that when you introduce names before the colon in a definition, you introduce that variable. Here is not necessary. So yeah, actually, yeah, we're just gonna copy and paste this. But it's essentially you just need the x to have a name here, and then the exponent you can just pattern match and get 1. Good. But before to let you go, let me go to the main page. Here we have, by the way, we have blocks, and we are describing some parts of the internals, how to compile VampIR through GEP. This is important if you don't want to go for the direct approach of compiling to circuits. This is a evaluation interpreter approach to compiling functional programs to circuits. And the other approach that we have is Juvix to VampIR directly. And in this case, we basically just take the program and remove all the features that VampIR doesn't support to compile to circuits. And we have a blog post about that, and it also takes you to all the examples, all the instructions. In the main page, we have this small example. So I said you take the Juvix file, you compile to VampIR, then you can go to Plonk or Halo 2. So you just need to specify the target, your file. This is your file, for example. Here we're just defining a hash function, is the meet-squared hash function. In this part, we have the definition of exponentiation by fast, is the fast algorithm, where you basically put the exponent in binary form and then perform stat. You can say that the program is terminating, and we have also pragmats for unrolling recursive functions, which is some of the challenges that we have when compiling to circuits. This is probably going to change. For the moment, you need to be explicit about how many times you want to unroll your functions. Otherwise, you cannot compile to circuits. Right. We're investigating how to remove this. We have some ideas. And the main function that you're going to compile to has one input in this case. It's NAT and will produce a NAT. And this is the instruction that you need to perform. So you take the VampIR, you do the trusted setup with the parameters, right? And then you specify that you're going to use Plonk, compile using the inputs. This is the output that we are heading. So in the code space, or well, if you don't have the code space, no, I think I need the code space. Okay. In the code space, you just can copy and paste this on your machine, and you will get, also taking the inputs, you will get the results. Let me see if this is already loaded. Okay. So there are many things that are missing, and other things. You can generate the proof with these commands and verify as well. That's part of the VampIR topic. Okay. Just before, just 1 second. Everything about Juvix is open source, so you can just go and see all the compilation parts. This is a really basic example of a Juvix. It's just comparing that the natural number is 0. And yeah, you can compile this to VampIR. If you want to know more specifics, I just can sit down with you and show you exactly what to do. If I don't know an answer, I can point you to the person that knows how to solve the thing, but I'm very confident that I can answer any technical question with more time. I don't have I think just have 1 hour. All right. I'm very excited. If you have any feedback, I'm really interested. If you want to use Juvix or any of the intermediate languages, We are doing integration with ZK LLVM. That's another project. And yeah, we can basically just talk to you about the internals and probably get more integration with the ZK ecosystem. So it's not limited to ANOMA, but is mostly focusing on providing the next language for ANOMA the apps. That's what I wanted to communicate today. All right?
Does anybody have any questions? Just raise your hand.
Is that a tardigrade up there?
Yeah, you're correct. So it's like an immortal specimen, yeah. So we hope Juvix don't die. Doesn't die.
I thought it'd be simpler.
Sorry?
I thought it'd be simpler.
The language.
Describing intents and conditional
Right.
intents, how I have to teach my users camel and how to do file errors.
Right, so that's part of our roadmap. Like, in the moment, you need to use this, let's call it primitive API for Taiga. And, but what is really important is that we are the designers of the language, the developers of the compiler, so we can change anything in the language. And of course, we want to make this much easier to follow. That's why we are including these syntax extensions and many other facilities for you to basically not write code.
I'm thinking about contracts. You want to create conditions to be filled. They can't synthesize a bunch of code and then get someone to compile it. They want like really basic stuff.
Yeah, we're going to get some applications, and what I foresee is that once we start doing those applications, we're going to change more the language. So far, we are just putting the ground for this technology.
What's probably missing, like the natural thing here would be time, because when you have an intent to exchange or do something, there's usually a time limit. It's like, I want to do it now, I want to do it. It's like in financial markets, you have an order to do a stock market order. It's, it's GDC, FOK, and you've got all valid until tomorrow, stuff like that. Because
But
intents have a timing anything. If I want to buy something and I want to trade this for a dolphin, I want to do it today, but tomorrow is another day, right?
oh yeah, but that's an issue that is not concerned to the language. It's more on the component that resolve the intents, right? So that which is actually quite a hard problem, computationally speaking.
You have an intent, you submit it. But then
Yeah.
what do you do if you want to retract?
To retract from the,
Yeah.
I don't know.
Because, maybe you want to buy a dolphin, but tomorrow you say, oh, no, I don't like dolphins.
All right. Yeah, I'm not really familiar with that scope of the application. Maybe you can answer, or I don't know. But, yeah, yeah, it's probably very concerning.
Any more questions?
Can you talk about the compilation to get? How is it different from compiling via VampIR? What is Get actually?
Yeah, so that's actually a quite interesting question to solve. So just for seeing this, we include, so we have a report about what is GEP, but it's essentially at the moment like a language for doing arithmetic circuits via categorical semantics, so to speak. So it's our alternative to not a direct compilation, as usually we will find with other programming languages that target circuits. So we basically observe that you can just see a language as a category, and then you have functors. So at some point, we want to evaluate the program that represents the circuit, and then in that sense, in that context, we want to avoid problems like the branching problem, right? So it's our detour in order to solve one of the issues that you basically will face when compiling to circuits. So yeah, GEP is this is I would describe it as an arithmetic language for the moment, using the categorical terminology, right? It's a category, like FinSet, basically. Yeah. But I can point you exactly what is the definition, which is not, yeah, the specifics. Yeah.
Just one question about the piano integers. Do you compile piano integers into the ZK server? Or
Yeah.
Do you map symbolic types to machine integers at some point?
So from the Juvix point of view, we just compile natural numbers to natural numbers to VampIR. But the in-house compiler, which is the one that takes the job, I'm not entirely sure what it's doing, but yeah. So the piano, this definition that I show about natural numbers is compiled to natural numbers. Sorry, to natural native. Yeah. There are other.
I think I missed something. What did you mention? Piano integers?
It's
Unary,
yes.
natural number notation. It's like the most inefficient way to
Yeah,
use
you don't
numbers.
exactly. You don't want to describe natural. It's just that this definition for natural numbers is convenient when you are defining functions by pattern matching, but you don't want to compile this like this way. But no, we have this annotation built in NAT, which tells the compiler that this type definition corresponds to natural numbers. So we have a special compilation phase for this.
And NAT is a big int of some sort. Is it,
Yeah.
How
Yes.
big is it?
How big is it? The last time that I tried, it ranged up to 2 power 62. Yeah. It's not, it's not 64 bytes, it's just 62. But we are planning in our roadmap to support big integers, which is challenging as well. Yeah. Any other question? No? Okay.